Introductory electromagnetics courses can feel like hitting a brick wall of math. You walk in expecting to study physics, and suddenly you are drowning in a new alphabet of symbols and operators. Today, we are going to untangle that syntax. By the end of this video, you will know exactly how to separate scalars from vectors and how to extract a pure unit vector from any 3D coordinate. Once you can confidently read and manipulate these mathematical structures, the actual physics of electromagnetics, the electric and magnetic fields, finally start to make sense. Let's start with the most basic data type, the scalar. A scalar is a quantity that is completely defined by its magnitude or amount. Think of things like temperature, mass, or the number on a car speedometer. It tells you exactly how much, but nothing else. But if you need to know where that amount is going, you need a vector. Compare that speedometer reading to velocity. A vector requires both a magnitude and a direction. So while our scalar was just 50 miles per hour, our vector is 50 miles per hour heading due north. When you take these individual quantities and map them systematically across an entire area, you get a field. A field is simply a mathematical function that specifies a particular quantity everywhere within a defined space. To visualize a vector field, imagine stepping outside during a massive storm. The wind whipping through the buildings has a specific speed and a specific direction at every single coordinate in that space. That continuous mapping of force and direction is exactly what a vector field represents. Identifying whether you are dealing with a simple scalar amount or a directional vector is step one. That single distinction dictates exactly what mathematical rules you must use to calculate their behavior in the real world. To perform those calculations, we need a reliable framework to track direction. For most introductory problems, that is the Cartesian coordinate system, our standard x, y, and z grid. This diagram shows the foundation of that grid. These base unit vectors, ax, ay, and az, each have a length of exactly 1. Any vector A in this space is built by adding its specific x, y, and z components along those axes. Once we have those three components, we find the vector's total magnitude, its exact length, by squaring them, adding them, and taking the square root. Now we take our original vector A and divide it by that total magnitude. We strip away the physical size of the vector. What remains is the unit vector, a value normalized to a length of exactly 1, representing nothing but the pure, isolated direction it is pointing. Let's execute this step by step. Here is our practice vector. Vector A equals 10 in the x direction, minus 4 in the y direction, plus 6 in the z direction. Step 1 is to find the overall magnitude. We drop our numerical coefficients, 10, -4, and 6, directly into our formula. We square them, add them to get 152, and take the square root for a total magnitude of 12.33. Step 2 is to isolate the direction. We take our entire original vector equation and divide it by our new magnitude of 12.33. We distribute that division to each individual component, 10, -4, and 6. This gives us our final unit vector, 0.811 ax minus 0.324 ay, plus 0.487 az. We have successfully normalized the vector. This new equation is the precise mathematical representation of the original vector's direction, scaled down to a length of exactly 1. When working through a long exam, it is incredibly easy to drop a negative sign or fumble a quick division step. If your unit vector is wrong, every calculation that follows it will be wrong too. To verify your work, run your newly calculated unit vector back through the magnitude formula. Square the components, add them up, and take the square root. If your math was perfectly accurate, the resulting magnitude will always equal exactly 1.00. Taking 10 seconds to do this quick self-check ensures your numbers are solid before you move on to the rest of the problem. Let's review what we've covered. Scalars are simple amounts. Vectors add a specific direction, and fields map those quantities. To isolate the pure direction of a vector, you find the unit vector by dividing its components by its overall magnitude. Now that you can identify and normalize vectors, you are ready for the next step, multiplying them together using dot products and cross products. If this breakdown helped clarify your physics homework, make sure to subscribe to the channel for more step-by-step engineering tutorials. Electromagnetics is a tough subject, But by mastering these basic vector operations right now, you have built the exact mathematical foundation you need to handle the physics that come next.